Hello everyone, I am Dave Wallace and I'm here to discuss to you about how to use Kirchhoff's laws in solving electric circuit parameters. So specifically, we will be using a simple problem to show you how to use Kirchhoff's voltage law and Kirchhoff's current law in solving parameters like power, voltage, and current. Okay, so here's the problem. So you have a simple network. We have a simple network composed of two ind independent sources, two voltage sources, independent voltage sources, and three resistors. They are connected as shown in your screen. So we are asked to solve for the current in each branch of this network, and also we are asked to solve for the power dissipated by each resistor as well as the power supplied by each voltage source. Okay. Now, using Kirchhoff's current law uh, and Kirchhoff's voltage law in solving network as shown on your screen before, we have at least 7 steps. So um, we need to first label its corner or node of our network with alphanumeric symbols. So in later we will be solving that one. We will be labeling each corner or node. Then second, we'll be counting the number of branch circuits as it will tell us the number of equations. So remember, the number of branch circuits is equal to the number of equations when using Kirchhoff's laws in solving uh, electric networks. We also need to count the number of nodes with 3 or more branches. So nodes with 3 or more branches, take note of that because that will tell us the number of KCL to be done when solving such problem. Okay. Then, of course, we will apply KCL and KVL to a particular part of the network. Then we will solve the equations we have after applying KCL and KVL. Then we analyze the network according to what is asked. Okay. So we I have prepared something here in Microsoft Paint. So this is basically the problem we have. So for the first step, we need to label. We need to label its corner or nodes. No, so in this case, this will be I will label this corner right here with A, this node here with B, this corner here with C, and this corner here with D, and we have E here, and we have F. Okay, so that's it for the step 1. So for step 2, uh, we need to count the number of branch circuits. So after we have labels A up to F, we need to count the number of branch circuits. So in this network, we have 3 branch circuits. So the first one will be from this node up to this node. We can have our branch current here. So basically, we can have our branch current here. We can call it our I1. Okay. That's basically our I1. Okay. All right. And then we have another branch circuit is from this node going to this corner, then up to this node. So this will be another branch circuit, and we will call this I2. Okay. Then from this node up to this node is another branch. So we have our third current here. I3. Okay. Okay. So we have three branch circuits. So this will tell us this problem can be solved with three linear equations. So three equations, three anodes, right? So that's why it's very important to really identify the number of branch circuit. So uh, if it happens that you will be solving networks with dependent sources, those sources with diamond symbols, the number of equations will be the number of branch circuit plus the number of dependent source. Okay, so but for now, for this problem, we only have three branch circuits, so we only have three equations. Okay, so this is one of the simplest problem we can have in this course. Okay, so we only have two power supply and power sources and three resistors. Okay, so we need to count also the number of nodes with three or more branches, so that we will know how many KCL are we going to do. Okay, so in this case um, we have two. We have a total of uh, four nodes. So this A, B, C, D, and everything here, D, E, F can be considered one node. So we have at least four nodes. But we only have two nodes with three or more branches which are connected. So that's node B and node C. So if you examine node B, we have three branches connected here. Basically, your I1, I2, and I3 are connected here, and your node E as well. We have your I1, I2, and I3 connected. Now, why is it important? So in the next step, that will tell us that we we have to make only one KCL, or else our equations will be null. No, so we will end up zero currents. We can solve zero currents. That's based on experience. Okay, so how to identify the number of KCL? It's the number of uh, nodes with three or more branches minus one. Okay, if it happens you have like four I mean two nodes with three or more branches. So wait, if you have if you have three nodes with three or more branches, three nodes with three or more branches for a more complicated problem, so you are expected to make two. So the number of nodes minus the number of nodes with three or more branches minus one. Okay. So, but in this case, there are two. So, 2 minus 1 equals 1. So, you will be doing only one KCL. So, since you have three anomes, because you have three branches, and uh, you will have one equation for KCL. So, that means you will be doing two KVL. Okay? So, that's crucial. Okay? I'll say it again. So, to know the number of KVL and KCL, it is important also to know the number of um, nodes, okay, and the number of branch current, okay. So let's start again. To get the number of equation, it is the number of branches, okay. So if it has dependent sources, the number of equations should be the number of branches plus the number of dependent sources, okay. So in this example, we have three. So we have two options uh, so we can have our equations. Okay, so we have Either we have a KVL or a KCL. Now, how to know the number of KCL? It's the number again, no, i- the number of nodes with three or more um, branches minus one. Okay. In this case, we have two. That's node B and node E. So therefore, we will have one KCL. So since there are three equations, we need to do two KVL. So uh, that's how we will make our equations. Okay, so let's do it. So going back to our step. So we're right here. We're right here. We're applying KCL. So applying KCL means we'll have to start doing our equation. So we have two options. Either we do your KCL here at node B or node E. So for me, it's always the one on the top because that's easier for me. So, right, should say KCL at node B, right? So remember, when doing KCL, the sum of current entering equals the sum of current leaving. So for node B, we have two currents entering, I1 and I2. So basically, it will result into, wait, that's I1 plus I2, right? Should be equal to your sum of current leaving node B, which is equal to only I3. So that's I3, right? So this will be our equation number one, okay? All right. Now, since we need three equations because we have I1, I2, and I3 to solve, so we need two KVL. So we start with KVL maybe here from corner F to A, then to B, then to E, back to F. So basically right here. So we'll be doing KVL here. So we will say KVL at loop. So that's at loop. Basically loop say F, A, B, E, F. So it has to be closed loop. So again, loop enters minus for this element here. Loop enters minus, goes out in plus. So that's positive voltage. So that's 48, right? So in this part of the network, this 5 ohm resistor, the assumed current direction is that way to the right, and the loop direction is also that way. So it has to be minus. Voltage drop here is minus. So basically that's 5 multiplied with the current, which is I1. Okay? And here, the loop direction is that way because we'll be having our KVL in this direction. The loop direction is also similar to the current direction. So we have also minus 10I3. Alright. And this will be equal to 0. And this will be our equation number 2. Okay? So, we have two equations now. One for KCL and the other for KVL. So, we need another equation. So, of course, we cannot use more KCL because it is restricted to the number of nodes. Okay? Minus the number of nodes with three or more branches minus 1. Okay? Now, we will do KVL in any in a different loop, different from your previous loop, right? So we try here. maybe from B to E, then maybe you start with B, C, D, E, right here. To show you it can be done this way. Okay, so we'll say KVL, right. So that's a KVL loop. Start with B, C, D, E, B. Back to B, right. So from here, from B to C, we have 2 ohms resistor. Remember, your assumed current direction I2 is opposite with your loop direction, because your loop direction is that way and your current direction is in the opposite way. So therefore, the voltage drop across your 2 ohms with respect to this Kirchhoff's voltage application of KVL should be positive. So that's why we have 2I2 here. Okay? So 2I2, right. Okay. Then loop direction is that direction, enters plus, exit minus, so that's minus 40 volts. So it has to be minus 40 here, right? And loop direction is opposite with the current direction, so that's plus 10 I think. Is equal to 0. Okay, and this is our equation number 3. Right. So we have 3 equations now with 3 unknowns. So of course we can solve this one. We need to rearrange these equations. If you will be using your calculator, so you need to rearrange your equations. So for the first equation, you will be having I1 plus I2, right, wait, I1 plus I2 minus I3 is equal to 0. And this will be our equation number 1, right? Okay. So for equation number 2, we have, of course, we can rearrange this equation, this one. We will, all negative terms will be transferred to the opposite side. So that's why we have 5I1, right? Plus 10. I3 is equal to 48. Okay. Right. Should be our equation number 2. And for equation number 3, we have, of course, the constant 40 can be transferred to the opposite side of the equation. So that we will have 2I2, right? Plus 10I3 is equal to 40. Alright. This will be our equation number 3. So, if you will use your calculator or any application you have, any software you have, any computing device you have, you will get I1 here, right? I1 is equal to 2.2 amperes. Right. So, I2 will be equal to, okay, 1.5 amperes. Okay. And for I3, we have 3.7 amperes, 3.7 amperes. Okay. So we have already done this one. We have already done this part. So we will now analyze the network. Okay. So we have we have calculated I1 equal to, which is equal to 2.2 amperes. This current right here. I2, which is 1.5 ampere, and I3 is equal to 3.7 ampere. So one way of checking if uh, your answers are correct, is that you will try to look at your currents. Okay, so for example, at node B, where you do your KCL, so your I1 and plus your I2 should be equal to I3. So if we take the sum of I1, which is 2.2, and 1.5, I2, which is 1.5, so of course it is equal to 3.7. So it indicates, now it is a sign now that you're doing your equations right. Okay, so if in case you at one point in your node the KCL doesn't hold, uh, so there must be something wrong with your KVL equations. Okay, so you have to take note of that. Okay, so but this time I would like to uh, tell you that we already have done this part. We have calculated the branch current of this network. We already have I1, I2, and I3. Okay, so basically if you are asked to solve for like power, for example, energy particular load is consuming or particular resistor is consuming, you'll start with solving your branch current. Okay, so this is how we do analysis with networks composed of one or more power supplies. Okay, so all right. So after we have completed this part of the problem, we will calculate the power dissipated by the three resistors and the power supplied by the two voltage sources. Okay? Alright. So we'll start with the 5 ohm resistor. Okay? So for the 5 ohm resistor, we'll call this one your P5, right? 5 ohm. Oh, wait, that's 5 ohm resistor. Okay. Uh, we'll call it P5. So basically, it's an I squared R loss. We can use I squared R. So that's basically the current flowing in your 5 ohm resistor is I1, so that's 2.2. I1 is 2.2. So that's 2.2 square I squared R, right? So, okay, that's 2.2 square multiplied with 5. Okay. Of course, this is um, 24.2 watts. Okay. For your 2 ohm resistor, okay. All right. So we will call it P2. Okay. So your P2 should be the square of the current flowing through your resistor times the resistance. Okay. So that's basically I2 squared times 2. So I2 is 1.5, so that's 1.5 square, right? Okay. 1.5 square times 2. 1.5 square times 2 is equal to 4.5 watts. Okay. And finally, we have for your 10 ohm resistor. So we call it P10. Okay. So that's the square of the current flowing through the 10 ohm resistor times its resistance. So this is basic Ohm's law. Okay. So the current flowing is 3.7. Okay, so that's 3.7 square. Okay, times 10. Okay, 3.7 square times 10. It's basically 136.5. 136.6. 136.9, by the way. So 136.9 watts. Okay. So the total power for all resistors, for all resistors. So basically we call it PT PTR for all resistors. So that's basically the power of the 5 ohm resistor plus the power of the 2 ohm resistor and plus the power of the 10 ohm resistor. So if you add up 24.2, 4.5, and 136.99, that's basically 165.6 165.6 watts. Okay. So that's for the three resistors. That's for the three passive elements of the network. Now, we will try to solve for the power of each voltage sources. So for the 48 volt source, right? So that's basically um, we call it P10 or P48 by the way. So that's P48, right? So since there is no resistance, power can be calculated by the product of the voltage and the current flowing through the current flowing. So we can take the product of the voltage across the generator and the current flowing through it. Okay, again, since there is no resistance, we can only uh, we can only compute for the power delivered or supplied or absorbed by the particular voltage source by getting the product of the voltage, which in this case is 48, right? All right, and multiplied with the current flowing through it, which is I1, which is 2.2. Okay. Now, if you do that, you will multiply 48 with 2.2. That's basically 105.6 watts. Okay. Now, for your 40 volt source, okay, we call it P40. Right. Okay. Again, you will have to get the product of your voltage 40 and the current flowing through it, which is 1.5. Okay. Of course, 40 times 1.5 is 60 watts. Okay. Now, if for all sources, we call it PT S. No? So basically, if we take the sum of the power supplied by your generator, 48 volt generator, and your 40 volt generator, it is equal to 165. 105 plus 6 plus 105.6 plus 60. So that's basically 165.6 watts. So this is not a coincidence, everyone. No? So this is not a coincidence. So it is an indication that what we have here are correct. So basically, uh, we have a source which supplied a total of 165 volt power, and all of those power are consumed energy in the process. So we're used by the passive elements, the three resistors, which has a total of 165.6 watts. Okay, so this is this is this needs to be highlighted right here and this right here. Okay, so this is not a coincidence. This is an indication that we are doing our calculation right. Okay, so I think that's all for this video. See you in the next video. Okay.